Welcome to AI Paper Slop, the YouTube series where we break down the AI and tech papers you actually need to know about.
Yeah, the ones that actually move the needle.
Exactly. And we are jumping straight in today. So the paper is on the scaling of PEFT towards million personal models of trillion parameters.
Right. This is the one published by MindLab back in May 2026.
Yeah, and if you're an ML engineer or researcher, or really just anyone trying to build AI agents that actually remember users without, completely bankrupting your startup.
Oh, yeah, the AWS bills are real.
Right? So here is the bottom line for you today. Parameter-efficient fine-tuning. So things like LoRA, they are fundamentally misunderstood by the industry right now.
Completely misunderstood, yeah.
You really need to stop looking at them as just like these cheap, budget-friendly hacks for fine-tuning when you can't afford an H100 cluster. Because this paper proves empirically that PEC is actually the architectural foundation for building persistent local states.
On top of shared foundation models, right? It's a complete paradigm shift, honestly.
It really is.
Because the researchers basically lay out the blueprint for moving from serving one monolithic kind of amnesiac universal assistant.
Which is what everyone is doing right now.
Yeah, exactly. Moving from that to serving millions of persistent trillion-parameter personal agents. And to do this, they prove we have to master three coupled physical levers.
Okay, so what are those levers?
First, scaling up the prior foundation model. Second, mathematically scaling down the adapter footprint so you can actually, host millions of them.
Right.
And then third, scaling out the population to leverage diverse collaborative intelligence.
So our mission today is to basically tear down the exact mechanics of how this all works. We're going to look at the hyperparameter transfer rules that make this physically possible without infinite compute.
Right, and dive into dynamic memory adapters like Delta-Mem.
Yeah, and also we need to unpack the actual physical infrastructure required to serve all of this in production without your servers literally catching fire.
Which is a very real risk, yeah.
Definitely. So let's start with a really striking biological analogy the researchers use, because I think it reorients how you should even be thinking about model architecture.
It's a great framing.
Right. So think about human DNA. Any two humans on Earth share over 99.9% of their genome. Yet that tiny fraction of, less than 0.1% variation, that produces the entire spectrum of human individuality.
Albert Einstein and, a professional wrestler share 99.9% of their source code.
Exactly.
Which is just a brilliant mapping to how we need to treat AI architectures moving forward.
How so?
Well, in this framework, the massive foundation model is that shared biology. It contains, more than 99% of the parameter weights.
Right, the base DNA.
Yeah, it provides the common competence, the baseline ability to reason, parse Python code, perceive images, call APIs, all of that.
And then the PEFT adapter is the tiny variation.
Exactly. That tiny LoRA file is the less than 1% of individual variation. It carries the instance-specific behavioral states. We're talking about learner preferences, structural habits, interaction memories, all that stuff.
Wait, let me stop you there and play devil's advocate for the engineers watching, because I know exactly what they're typing in the comments right now.
I bet I know what it is.
Yeah, they're saying, does this mean the adapter is just a replacement for RAG? Like, if I have a local personalized adapter, am I just supposed to bake all my company's PDFs and personal databases directly into those tiny weights?
No. And that is a critical distinction the paper explicitly bounds. Do not use PEFT to replace retrieval for raw facts.
Okay, so keep the vector databases.
You still absolutely need retrieval augmented generation for your internal documents, exact quotes, database lookups. The adapter is not a filing cabinet.
Right.
The adapter acts as a compact, trainable unit of adaptive state. It dictates how the model behaves and reacts based on its experience with you.
Okay, so RAG is the messy desk full of papers, and the adapter is the highly specific, caffeinated workflow I use to sort through it.
That is a great way to put it, actually.
To our RAG is what the model knows. The adapter is how the model acts.
Exactly. It isn't storing the raw text of a financial report you read yesterday. It's storing the deeply ingrained, learned preference that you always want your financial summaries in a 3-point markdown list.
Right, and that you get annoyed if the model uses, overly flowery language.
Yeah, and this behavioral state is what allows a model to preserve true continuity with a user over repeated sessions.
Okay, so if the foundation model is our shared DNA, logic dictates it needs to be incredibly capable for that tiny fraction of an adapter to actually do anything useful.
Absolutely.
Which brings us to the first massive engineering hurdle, making the base model as strong as physically possible.
And this is where we get into the operationalization of trillion-scale LoRa with reinforcement learning.
Okay, lay that out for us.
Well, when you apply RL to a fixed adaptation budget, meaning you freeze the massive base model and only update the tiny adapter, your RL is inherently prior limited.
Prior limited meaning it can't magically invent a capability the base model doesn't already have.
Exactly. RL can only reinforce trajectories that the current policy can successfully sample. So if your base model is weak and can't, reason its way out of a paper bag,
then your tiny adapter can't manifest complex reasoning out of thin air.
Right. But if your base model is a trillion-parameter giant that already knows how to execute complex multi-step logic, a tiny, cheap tweak in the adapter can redirect that latent capability.
It produces a massive, highly customized behavioral shift.
Exactly. A stronger base model gives you a vastly superior surface area of latent capabilities to leverage.
But let me push back on the reality of actually doing that. Because at small scales, like a 7 billion parameter dense model, running RL with LoRa is basically a weekend project now.
Sure, yeah.
But this paper is talking about trillion parameter MoE, or mixture of experts scale. If I try to run RL on a trillion parameter MoE and only update a LoRa adapter, doesn't the entire system just violently explode?
Oh, it absolutely does.
I thought so.
Yeah, the paper goes deep into these scale-induced failure modes. At the frontier MoE scale, discrepancies that you would completely ignore in a small, dense model compound into just catastrophic algorithmic failures.
Give us an example of that pipeline.
Think about the life cycle. You have rollout generation, then scoring, then training, then checkpointing, and finally serving. In a small model, minor numerical mismatches across that pipeline just mean your loss curve wiggles a bit.
But in a trillion parameter MoE,
it destroys the model.
Unpack that. Why? What is actually physically happening inside the MoE architecture that causes it to break like that?
Well, think about how a mixture of experts works physically. It is a massive, highly sensitive switchboard.
Right, with all the different specialized routing.
Yeah, the routing mechanism sends specific tokens to specific expert networks based on tiny variations in the latent space. If the policy that generates the trajectory during your live rollout differs by even a fraction of a decimal from the policy whose probabilities are being scored during training, you lose semantic continuity.
Oh, I see. So a token that was supposed to get routed to the coding expert suddenly gets misdirected to the creative writing expert.
Exactly.
Because the adapter shifted the math just enough to cross a routing threshold.
Yes. And by the time the reinforcement learning algorithm tries to score that trajectory to calculate the update, it's looking at a completely different computational path than the one that was actually rolled out.
So your KL drift, that divergence between your reference model and your active policy, it just absolutely explodes.
The routers get totally confused, the optimization collapses, and your adapter becomes complete garbage.
Wow.
Yeah. So the paper proves that to scale up this prior, you have to engineer strict semantic continuity across the entire distributed execution pipeline.
You need systems-level orchestration.
Exactly. To ensure the adapter semantics are mathematically identical at the rollout server, the training node, and the inference engine.
Okay, so let's assume you survive that engineering nightmare. You stabilize the KL drift, you maintain semantic continuity, and you now have a massive, highly capable MoE base model.
Which is a huge achievement.
Great. But now you have a massive budget problem.
Yeah.
If I'm AWS or a startup hosting 1 million distinct users, I can't afford to store a 5 gigabyte memory state for every single person.
Oh, absolutely not.
AWS is going to send me a fruit basket, but my startup will be out of runway in a week. So how small can we physically compress this adapter before it just gets amnesia?
So the researchers ran some incredible experiments on rank reduction to find the physical floor of this adaptive state.
What did they test?
They trained adapters on complex reasoning tasks, stepping the LoRA rank down from 256 to 64 to 16, all the way down to rank 1.
Wait, rank 1. At rank 1, you basically have enough parameters to store the user's first name, maybe? Doesn't the loss curve just look like a flat line?
See, here is where the data gets wild. When you drop down to rank 1, the mean performance score across different training seeds does completely collapse. It looks like a total failure.
Okay, yeah, that makes sense.
But if you look at the best score across those random seeds, it remains incredibly competitive with the high-rank models.
Hold on. If the best seed is still passing the benchmark, that means the raw physical capacity to learn the task is literally still there inside a rank 1 adapter.
That is the pivotal insight. The bottleneck for tiny adapters is not a lack of expressive capacity. The bottleneck is across seed reliability.
Because the optimizer is just wandering around in the dark.
Exactly. The parameter space is so heavily constrained at rank 1 that standard optimization struggles to find a good solution consistently.
So the engineers aren't hitting a hardware limit, they're just getting unlucky with the math.
Yes, a rank 1 adapter with standard weight initialization is essentially just a lottery ticket.
Wow, so how do you fix it?
Well, to rescue this tiny adapter regime from being purely luck-based, the researchers explain you need strong RL native initialization. Standard Gaussian noise initialization just won't cut it.
It has to be geometrically aware.
Right, aware of the RL objective to ensure optimization stability from step 1. If you fix the initialization, you can drastically shrink the adapter footprint.
Giving us that ideal world where the individual variation is tiny but entirely robust.
Exactly.
But let me challenge this from the perspective of the engineer who actually has to deploy this. Because if you're operating millions of customized adapters, you cannot run hyperparameter sweeps to find the perfect learning rate for every single user.
No, you'd go bankrupt just doing the tuning sweeps.
Right. So if I decide to drop my system's adapter rank from 64 down to 4 to save server space, how do I know what learning rate to use without spending a fortune tuning it?
The paper introduces a massive quality-of-life theoretical fix for this. They call it the square root rule for hyperparameter transfer.
Okay, how does that work?
They prove empirically that your learning rate, let's call it alpha, should scale proportionally with the square root of your LoRA rank, R.
Alpha is proportional to the square root of R. Break that down for me physically. Why a square root? What is happening to the matrices there?
It's all about stabilizing the magnitude of the updates to your hidden states. When you change the rank of a LoRa adapter, you are changing the inner dimension of the matrix multiplication.
Right, you're changing the size of the pipeline.
Yeah, so if you just naively drop the rank from 256 down to 4, you've drastically reduced the number of pathways contributing to the final output vector.
Meaning, if you keep the same learning rate, your updates will be far too weak because fewer parameters are pushing the needle.
Exactly.
It's kind of like trying to steer a heavy truck with the sensitive steering wheel of a sports car. The input doesn't match the physical mass of the vehicle.
That's a perfect analogy. So by scaling the learning rate by the square root of the rank, you mathematically create a rank-invariant early step proxy.
Right.
The effective magnitude of the changes made to the model's hidden states remains perfectly consistent, physically, regardless of whether your matrix is rank 4 or rank 256.
Oh, wow. Meaning I can run a cheap tuning sweep on a small sample of rank 64 adapters, find a great learning rate band, and then safely drag and drop that exact same recipe across my entire massive population of rank 4 adapters without changing anything.
Exactly. The transferability is literally built into the physics of the update rule. You don't have to tune per instance.
That is going to save someone listening $1 million in compute.
Without a doubt.
But the paper doesn't just stop at optimizing these static LoRA weights, right? Because if we're talking about a true personality, it can't just be frozen in carbonite after an offline RL run.
Right. It needs to react to what you told it 5 minutes ago.
Exactly.
Which is why they push the boundary of the architecture by introducing something called Delta-Mem. This moves us away from static parameterization and turns the adapter into a genuinely stateful, writable memory bank during live inference.
Unpack that delta rule learning physically. What is happening in the attention heads while I am chatting with this model?
Normally, your adapter weights are frozen during inference, but Delta-Mem sits parallel to the frozen weights as a compact online memory state.
So it's active while you chat.
Yeah. During a conversation, as it processes your new context, it uses a fast weight delta rule during the forward pass. It essentially reads its current state to produce history-dependent, low-rank corrections to the base model's attention computation.
And then it updates itself.
Yep, it iteratively updates its own local matrix based on the residuals of that interaction.
So it's absorbing the context window into its own localized weights on the fly without needing a costly backpropagation run. It's like a living document.
Yes, you've successfully built an adapter that accumulates interaction history efficiently.
Okay, let's take a step back and look at the whole board here. We have a monster-based model that gives us leverage. We have impossibly small, highly reliable, stateful Delta-Mem adapters, thanks to the square root rule and geometric initialization.
Right, all the pieces are there.
So what happens when we turn on 1 million of these at once?
This brings us to the population scale. The researchers looked at the OASIS social simulation experiment to see what a population of persistent adapters actually does.
Okay, OASIS.
Normally, when researchers simulate an AI social network, it's just a monolithic feed. You take one single model, sample it repeatedly with a high temperature, and use different prompt injects to pretend they are different users.
Which always feels hollow to me. Prompt-based personas collapse so quickly. They don't have deeply ingrained grudges or long-term behavioral attractors. They're just wearing masks.
Exactly, because they are all ultimately governed by the exact same algorithmic valley. But with PE adapters, you create genuinely persistent actors. Each adapter has its own distinct training history and its own physical weight topology.
So the personality acts as the environment itself.
Yes. How these different adapters react to the same piece of information actually structures the topology of the simulation organically.
Oh.
You get real echo chambers, genuine ideological clustering, and complex behavioral patterns that a single monolithic model physically cannot simulate.
That is super fascinating for a sociology paper, but let's talk hard performance. If I'm an ML researcher trying to beat a benchmark, does having a room full of different personalities actually make the AI smarter at solving complex math and logic problems?
It does, and this is actually the most quantifiable hard data finding in the paper. They call it the model count scaling law.
How did they test it?
They ran a controlled experiment using the Qwen 330B model. They trained up to 200 distinct LoRA models on a math dataset and then aggregated their answers using a majority vote.
Hold on, I'm going to play the skeptic again here.
Go for it.
If you were just taking a majority vote from 200 variations of the exact same base model, how is that any different than standard stochastic decoding? Why wouldn't I just take the single best base model, crank the temperature up to 0.9, sample 200 different answers, and take the most common one? Stochastic decoding is practically free compared to orchestrating 200 different LoRA files.
That is the exact counter-argument the researchers anticipated, and they dismantled the sampling noise argument purely with empirical data.
What does the data show?
When you repeatedly sample from one single model with high temperature, which is the repetition baseline, the performance plateaus rapidly. In their tests, the accuracy for single model repetition maxed out and totally converged at 43.3%.
So cranking the temperature stops helping. Why is that?
Because of underlying algorithmic bias. A single model has a specific manifold of high probability paths it likes to take. Turning up the temperature just adds noise to those paths.
It doesn't invent new ways of thinking.
Exactly. You're stuck in the same valley, just bouncing around slightly differently.
It physically cannot think outside its own box.
Right. But when they collaborated across the distinct LoRA variants, the accuracy did not plateau at 43.3%. It kept scaling, eventually hitting 48.7%.
Wow, that's a huge jump.
It is. The adapters created entirely different valleys of probability. The researchers established an empirical logarithmic scaling law from this data.
What's the formula?
Accuracy is roughly equal to 0.386 plus 0.0172 times the natural log of k, where egg is the number of distinct collaborating adapters.
Let me make sure I'm getting this. Just by introducing adapter diversity, which you can create artificially just by shuffling the training data order, changing the masking, or taking checkpoints at different epochs, you create complementary policies.
Yes.
They make different mistakes, they have different blind spots, and they have different strengths.
Yes. And when you aggregate them, these highly specialized, slightly flawed individual policies completely crush the repetition of one centralized policy.
So diversity itself becomes a quantifiable mathematical unit of scaling. You aren't just scaling raw compute, you are scaling the collective intelligence of a population.
Exactly. It's brilliant.
This all sounds incredible in theory, but we really have to address the elephant in the room here. Managing 200 models, let alone a million, sounds like an absolute infrastructure nightmare.
Oh, it is. Or it was.
Right, because all of this beautiful math and log scaling is completely useless if you can't build the physical server architecture to support it. And the paper introduces a systems layer called Mint to solve this. How does it work?
The systems layer is the absolute linchpin. If you don't have an infrastructure like Mint, the failure states across everything we just talked about are absolute.
Right.
If you scale up the base model without lifecycle management, you train a massive MoE adapter once, but you can never reliably update it. If you scale down the adapters without mobility, your serving infrastructure will still treat them like giant, independent, monolithic files.
And you end up copying an 8 gigabyte base model into VRAM every time a user logs in.
Which means your AWS bill goes to the moon.
And if you scale out the population without addressability, your server room basically turns into a graveyard of millions of orphaned LoRa weight files that you can't track, selectively load, or roll back. It's totally unmanageable.
Exactly.
Yeah.
So the architectural shift Min proposes solves this by strictly separating the identity of the adapter from its residency on a GPU.
Identity versus residency. Give me a physical analogy for that.
Identity is the passport and the blueprint. It's the metadata policy record. It tracks the provenance, the exact base model it belongs to, the training rollout data, the target modules, and its semantic definition.
Okay. And residency.
The residency is the physical body. It's the actual physical adapter weights loaded into GPU memory to do active inference using something similar to page attention.
So you aren't passing around full models across the network. You are just pinging tiny policy identities and instantly materializing the resident weights on top of a frozen base model already sitting on the GPU.
Exactly.
Let's give the audience the hard numbers from the paper to show why this physical separation is so powerful. Because for a Qwen 3.4b model, if you try to swap a full merged checkpoint, you are moving over 8 gigabytes of data.
Right.
And that takes about 71 seconds to materialize on the GPU. You obviously cannot do that on the fly for millions of users chatting in real time.
No, the latency would be unacceptable. But look at the adapter-only handoff that Minty's residency system enables. For that exact same Qwen 3.4b model, a rank 32 LoRA adapter artifact is only 252 megabytes.
And the time it takes to load it?
Just 0.036 seconds.
36 milliseconds.
36 milliseconds.
Yeah.
And that translates directly into massive serving performance gains.
Right, because the total sample speed for the full model merge took over 55 seconds to generate.
Well, the adapter-only handoff achieved the exact same generation in about 4 seconds.
That physical reality, the ability to physically load, unload, and hot swap an entire behavioral state into VRAM in milliseconds is what allows thousands of personalized models to share a single inference runtime instantly, request by request.
It's what makes the million-model vision actually viable on standard commercial hardware.
Which brings us full circle. So thank you for tuning in to AI Paper Slop today. Let's quickly recap the core value for the engineers and researchers listening.
Sounds good.
PFT is not just a hack for saving VRAM. Through the precise orchestration of scaling up the foundation prior, scaling down the adapter footprint via mathematical rules like alpha proportional to the square root of r,
And utilizing writable states like Delta-Mem.
right, and scaling out the population for collaborative voting, we now have a literal blueprint for highly personalized, persistent AI ecosystems.
It is a profound shift from how the industry's operated for the last 3 years, honestly. We are moving away from treating models as static, locked, universal oracles.
And moving towards viewing them as shared biological substrates that host billions of unique digital minds.
Exactly.
And before we sign off, we want to leave you with a final thought to mull over, building on the hard math we covered today.
Yeah, think about this. If we accept that logarithmic scaling law of collaboration we talked about,
The proven idea that aggregating diverse, specialized LoRA adapters consistently and mathematically beats single model sampling.
right, if we accept that, what happens to the overall AI race? Right now, every major lab is burning billions of dollars and megawatts of power to train one marginally larger, universally capable monolithic God model.
But if diversity scales better than sheer size, the true path to artificial general intelligence might not be a single oracle at all.
It might actually be utilizing the collective intelligence, the continuous voting, and the organic, messy debate of millions of highly specialized, slightly flawed, but completely unique personal models.